The purpose of this screencast is to say a little bit more about booleans. Now in Java, a boolean is a primitive data type similar to int and char and float and so on. And it has only one of two values. It's either true or false. And it's named after George Boole, a 19th century British logician. And we've already seen many examples of expressions that can have Boolean values. So the simplest is to have just a true or a false. We can do tests, sensors on a bugle, such as Becky is over bagel, or Peter Parker is facing wall, or say Spidey is facing a trail that's green in color. We can also have variables whose values are Booleans. So for instance, here we declare a variable called flag whose value is true. And what that does is that describes a box whose name is flag and which holds the value true. Similarly, we can have a variable named result that holds the value of this Boolean expression. So this Boolean expression, get cell color equals C, finds the color of the cell under the current bugle, sees if it's equal to the color named C, and that's either true or false. It takes that result and puts it into a box named result. So that true or false goes into a box. And here we declare a Boolean at wall. So that's just the name of a box. And that will contain, later on, contain the value of whether the green goblin is facing the wall. So that's either true or false. So we can stuff a true or false into a box in all of these ways. One of the ways we can get Booleans in Java is to test two values for equality. The simplest kinds of values we can test are things like integers. So for instance, is 1 equal to 1? The answer to that is true. And for this purpose, we use the double equal sign, which is pronounced equals. So the reason why we didn't use the name equals for the single equal sign is because it's the double equal sign. It's pronounced equals. A single equal sign is pronounced gets. Now some people say equal or double equals, but we're going to just call it equals in this course, because mathematically the notion of equality is that you're testing two values for the same, to see if they're the same. Is the number 1 equal to the number 2? No, that's false. We can use the equals to test other values. So is the value false the same as the value false? Why, that's true. Is the value true the same as the value false? Why, that's false. Now, for more complicated values, such as objects, we can test their values in different ways. So we can use equals on objects to test to see if they're the same object in object land, which is actually not usually what we want. Usually we prefer to determine if two objects have the same components, which we use the dot equals method for. So for instance, two locations are considered to be dot equals if they have the same x and y coordinates. Two colors are considered to be dot equals if they have the same red and green and blue components. And two bugles are dot equals if they have the same positions, headings, colors, and brush downs. Let's see this via an example. So here we'll do an example to show the difference between equals and dot equals. We'll begin with an object land that contains three objects. The first is a location L1 with x coordinate 1 and y coordinate 2. We have location L2, which has the same x and y coordinates as L1, but is a different object. And a location L3, which has x coordinate 3 and y coordinate 4, which are different components than the other two locations. Okay, and now we'll consider an execution frame in which we have a variable p that holds the value of L1, location L1, variable q holds location L2, r holds location L3, and s holds location, which is also L1. Now, is the value in P equal to the value in P? Are they the same object in object land? Well, they're both the location L1, so the answer to that question is true. We'll write a T for true. How about P and Q? Well, even though they both denote the location 1, 2, they are different objects in object land. Location L1 is a separate object from location L2, so we're going to write a false there. How about P and R? Well, they're clearly different locations. They even have different components, so that's clearly false. And how about P and S? Well, P and S contain the very same location L1, so the answer to that is true. Now, how about for dot equals? Dot equals on locations test if their coordinates are the same. So for any two elements that are equals, they are definitely dot equals. So certainly, since P is the same location in memory as P, they are definitely dot equals. So that's true. They have the same x and y coordinates, clearly. Even though P and Q are different locations in object land, they have the same coordinates. So even though they are not equals, they are dot equals. P and R, however, have different locations, so that's false. And P and S, they're the same location in memory, so this is true. We have other ways to compare numbers other than equality. For instance, we have operators such as less than or equal to, not equal, greater than or equal to, or greater than. So let's see some examples. Is 3 less than 4? That's true. Is 3 less than 3? No, that's false. But 3 is less than or equal to 3, so that's true. Is 3 not equal to 3? That's false, because they are equal. Is 3 not equal to 4? Yes, that's true. They are not equal. Is 5 greater than or equal to 5? Yes. Is 5 greater than 5? No, that's not true. Is 5 greater than 4? Yes, that's true. We also have Boolean operators that can combine the values of two Boolean expressions. The first such operator is the conjunction or AND operator, which is written as two ampersand signs and pronounced AND. So we say expression 1 and expression 2. And the value of this AND expression is true if and only if the values of its two sub-expressions are true. Let's look at an example. Suppose we say is facing wall and is over bagel. Well, in the first scenario here, our bugle, in fact, is facing a wall, and it is over a bagel. So we have true and true, so that is true. If the bugle is facing a wall but is not over a bagel, then since both things are not true, the result of combining them with conjunction is false. In the third scenario, the bugle is not facing a wall, and so no matter what else comes after it, it can't possibly be true, and so it must be false. And the same is true in the last situation. Since it's not facing a wall, the result must be false. And is not the only way to combine two Boolean expressions. Another way to combine them is via OR, which is written as two vertical bars and pronounced expression 1 or expression 2. And this combination is true if either one or both of the sub-expressions is true. So let's consider our scenarios again. Here we have a bugle which is facing a wall, and since at least one of the expressions is true, it will definitely be true. And the same is true in the second case. It's facing a wall, so it's also true, regardless of what, it's over a bagel or not. In the third scenario, it's not facing a wall, but it is over a bagel, so since at least one of the operands is true, the result is true. And in the final scenario, it's neither facing a wall nor over a bagel, so it's false in both cases, so the result of that is false. Our final operator is the negation operator, which is written as an exclamation point and is pronounced not. So exclamation point expression is pronounced not expression. And it inverts the meaning of the Boolean expression. So not of true is false, and not of false is true. So for example, let's consider the expression not facing wall. Since in both the first two scenarios, the bugle is facing a wall, if we negate that, the result is false. In both of the second situations, the bugle is not facing a wall, and so those values are true. These operators can be combined in arbitrary ways. Let's consider some examples. Our first example is this, in which we are combining the not of is facing trail color green with the is over bagel with the and operator. Now note that the not binds more tightly than the and. It has what's said to be a higher precedence, so that the expression parses in this way. So in the first scenario, we are in fact facing a trail that's green, and so not facing a trail as green is false. And regardless of what we combine false with a conjunction, the result will be false. In the second scenario, we are not facing a trail that's green, but we are not over a bagel. Is over bagel is false, so in fact that's also false when we combine them. In the third scenario, we are facing a wall, so we are not facing a trail that's green, and we are over a bagel. So we have true and true to get a true. And in the fourth scenario, we again are not facing a trail that's green, and we are over a bagel. So the result of that is true. In our second example, we are going to calculate is facing trail color green and combine it with is facing wall with an or, and then after we do the or, we are going to take the not of those two. So for example, in the first scenario here, we are facing a color green, that's true, and no matter what we or that with, we will get a true, but we're going to take the negation of that, so that's a false. In the second scenario, we are not facing a trail that's green, nor are we facing a wall. So we have two falses, and the or of that is false, and if we negate that, we get a true. In the third scenario, we are not facing a trail that's green, that's false, but we are facing a wall. And so that combination is true, but if we negate it, we get a false. And finally, in the fourth scenario, we are not facing a trail that's green, nor are we facing a wall. And so the combination of those is false, but we are negating it to get a true.